So click on supervised machine learning, and inside supervised machine learning, I have a folder, support vector machines. Click on this folder, and here I am at my project 1. So if I click on this file, it will be open in Google Colab environment. So here I am at my project 1 for support vector machine. So in order to solve this project, I will import NumPy, I will import pandas, I need a seaborn, matplotlib, and I also need a function make_blob. So I will import this function from sklearn.datasets. So let's run this cell to import all these necessary Python files or libraries. Now it's time to generate the data. Now we have already seen this function, that how this function works, make_blob. So in order to create the data set, that is in order to create the feature matrix and labels, we are going to use make_blob dataset. We have used this dataset in our section on KNN. Okay, so the first input is the number of samples. So we are going to generate 100 sample, and we are going to generate 100 samples with 2 features. Centers is equals to 2 means that we want 2 labels in our data set. The cluster standard deviation is 1.5. So this value, the cluster standard deviation, will separate the 2 centers with some distance. And this is random state is equals to 42. We know that if we set a random state, we will be able to generate the same data points every time we run this cell. So if I run this cell, we will get 2 kind of outputs. That is, we will get the labels and we will get the feature matrix. Okay, we can see these values. So if I write XB and if I run this cell, I will be able to see my feature. So this is my XB, and we can see that we have samples, we have first column and second column. So this is our first feature of the data, and this is our second feature of the data, because we have set n samples is equals to 2. Similarly, we can see YB, that is the labels, and if I add another code cell here, and if I run this code cell now, so I can see that I have 2 kinds of label, that is 0 and 1. Since we have set centers is equals to 2 here, it will ensure that we should have 2 label, that is 0 and 1. So in this way, we have used the function make_blob in order to generate the data set. Now we have these data samples with 2 features, and we have labels and 2 kinds of labels, that is 0 and 1. Now it's time to visualize the data. For visualizing the data, I have set the figure size 8:6. So what I am going to do, basically, I am plotting the second feature against the first feature. So basically, this is the value of the second feature, and this is the value of the first feature. So I am going to plot a scatter plot between the second feature of XB and the first feature of XB. So here is the line of code. This is the second feature of XB. This one will ensure that I will extract the second feature from XB, and this is the first feature of XB. So I am going to plot a scatter plot between them. Okay, this is my X label and Y label. The title of the plot is data visualization. And here I am getting the information. GCA stand for get current axis. So we have X axis and we have Y axis. So here we are getting the information about the X axis and Y axis in order to set the limit for those axes. So you can see that X limit is equals to axis dot get X limit and axis dot get Y limit, which we obtained from here. And here we are observing the data. Okay, so this is the data visualization. We can see that we have 2 labels. That is, here the labels are plotted with red and with yellow color. And we can see that there is a perfect separation between these labels. So this is according to the data which we have generated. Okay, so this is a scatter plot between the first feature and the second feature. We can see that this is the first feature and the second feature. So this is the scatter plot between the 2 features of a data. Okay, now we want to draw the best line to separate the classes. We know from the concept of support vector machines that we can draw as many lines as possible between them, but there is only a one line which is the best fit line. How to draw the best fit line? So we know that this is the equation of best fit line, y is equals to mx plus b. So how I am going to set the best line? So I am generating the value of x which are linearly spaced between -6 and +6. Here I have generated a list. This list has basically 5 pairs. Every pair belongs to one line. So basically I am going to draw the 5 decision boundaries or 5 lines between these two classes because I have 5 pairs. So in each pair, the first value is the value of m, that is the slope of the line, and the second value is the value of b, that is the intercept of a line. So I have x, I have slope, I have intercept, and I can use this equation y is equals to mx plus b. After calculating y from mx and b, I will plot y against x. Okay, let's run this cell. In this cell, first we create or first we plot our data set again. Then on top of our data, we are going to plot the best fit line. Okay, let's run this cell to observe these things. Okay, now we have the data set, we have a red sample, we have the yellow sample, and now these are the 5 lines between these two labels which can classify or which can separate this data. So we can see that the center line is always best because it has a maximum margin on either side of the labels. Okay, so this is one of the method of drawing or fitting the best line to our data. Okay, now it's time to import support vector classifier or support vector machine. So from sklearn.support vector machine, we are going to import support vector classifier. So here I am importing support vector classifier, and here I am instantiating support vector classifier, and I am calling it SVC. So if you see here, I did not pass any input parameter because till now I don't know what kind of input parameters I can pass to this SVC. Okay, in order to see the input parameters, we have to call the help function on SVC. So let's run this cell. When we will run this cell, we will import SVC, we will instantiate SVC, and we will also able to see the string document or the document about the SVC. So let's run this cell, and we can see that here is the document of SVC. Let's see the important input parameters that could be passed to this SVC. Okay, so we are here. Now we can see that in SVC, the first important parameter we can pass is C. Now student, this C is same as that of K, which we study in support vector machine. We know that K is the most useful parameter in order to control the functionality of support vector machine. So if we increase K, it means support vector machine will become a hard classifier. And if we decrease the value of K, support vector machine will become a soft classifier. Furthermore, this C is also used to perform the regularization of the support vector machine. So here is the information about C, that its default value is 1, and here they are calling it as a regularization parameter. So we have learned this as a K in our theory, that K is our regularization parameter, and it also controls the amount of maximum margin. Okay, the another important input which could be passed is the value of kernel. So the default value is radial basis function. If we do not pass anything here, then C is 1, kernel is RBF, and the third important parameter is a gamma. Gamma is a scale. So here gamma is equals to scale is the default value. So basically gamma is the coefficient that is used with kernel in order to control the working of the kernel. So we have two possible values of a gamma. Here we have gamma. First we see what kind of kernel we can pass. So RBF is the default value. The other kernels are linear kernel, poly kernel, sigmoid, and pre-computed. Okay. The other thing is the gamma has two possible values. Basically three possible values, that is scale, auto, or we can pass any value which should be a float. Okay, the default value is scale. So the thing is, if gamma is equals to scale, then this is the equation of a gamma. On the other hand, if we use gamma as a auto, then it will use 1 over number of features. That is, if gamma is equals to auto, it means this value of gamma will be 1 over number of features. Suppose if we have 2 features only in our data set, in that case, the value of gamma will be 1 over 2, that is 0.5. But in case the gamma is scale, here we have to multiply the number of features with the variance of the data, and then we will divide it by 1 in order to get the value of gamma. So if gamma is equals to scale, it will use this equation in order to find the value of a gamma. If it is auto, then gamma will be calculated using 1 over number of features. So these are three important parameters, that is the gamma, the kernel, and the value of C. Okay. Now, if we scroll down, we have learned that C is a regularization parameter. Here in support vector classifier, the strength of regularization is inversely proportional to C. So this C is same as K we study in the theory of SVM. This is our K, which we have studied in our theory of SVM. So larger the K, larger will be the margin, and support vectors are further away from this hyperplane or the decision, and the margin is called the hard margin. So we have studied this all in the mathematics of support vector machine and in the analysis of the variable K, that how K can be useful in order to make the support vector machine as a soft or a hard classifier. So this C is same as K. Okay. Now apply support vector classifier for large value of C. So basically we are taking C is equals to 1, which is considered as a relatively large value. The kernel we are going to use is a linear because we want to perform a linear classification first. Here I am fitting my support vector machine to my data, that is XB and YB. Let's run this cell. So I have fit my support vector machine. Now student, here is the function in order to draw the hyperplane of support vector classifier. So basically what we are going to do in this function and what we want this function to do. So here I am defining a function called draw underscore support vector classifier underscore hyperplane. So this function will use to draw three hyperplanes. Okay, this is the situation. So I want this function to draw three hyperplane. That is, one is the decision boundary, the other is a hyperplane for the class, and another is the hyperplane for the other class. Since we have two classes, so we need two hyperplane for the classes, and one is our decision boundary. So basically we need in total 1, 2, and 3. We need three hyperplanes. So that function will help us to draw the three hyperplanes. Okay, so what are the input to this function? The input is the support vector classifier, the features of the data, that is X, and the labels of a data, that is Y. So here I am setting the figure size. Here I will plot the second feature against the first feature. And here is the title, that is support vectors and hyperplane. Now here comes the important part. Here I am getting the information from the current axis. GC stands for get current axis. Based on the current axis value, I will set the limit for the x-axis and y-axis. Now, these line of code, if you see, we have three variables, I, J, and K. So basically, these three variables will ensure that we are able to draw the three hyperplanes. So every variable controls one of the hyperplane. Okay. And here are the colors of hyperplane. If you see I, J, and K, these are the three variables which controls three hyperplane. And these are the color of the hyperplane, red, magenta, and yellow. Okay, these are the line style. So the decision boundary will be a straight line and other hyperplanes will be the dotted line. So this is the line width. Okay. Furthermore, in addition to hyperplanes and in addition to the line style, which is this kind for the decision boundary, and this is the dotted line for our hyperplane, we also need support vectors to be shown on their respective hyperplane. That is, a support vector, if support vector belongs to positive class, then it should be drawn on the positive hyperplane. And if the support vector belongs to negative class, it should be drawn on the negative hyperplane. So here we are ensuring, here we are drawing the support vector. If you see, here we are drawing the support vectors on the first hyperplane and on the second hyperplane. We know that we do not need support vector on a decision boundary. Therefore, we have only two kind of support vectors for two hyperplanes. Okay, so this is the edge color of the support vector, that is, it is a green color. So this is the description of the code, which is a function which help us to draw this kind of figure on our data set. So since we have studied this figure in our theory, therefore we want to draw this in Python as well. Okay, now it's time to draw this. Now I am observing support vectors and hyperplane. So here is my function, draw SVC hyperplane. If I go back to the function, it needs 3 input. That is, it needs support vector classifier, it needs XB, and it needs YB. So let's run this cell. So if I run this cell, it will draw a support vector. Now you can see that this is a beautiful figure, and we can see that this is our red class, this is our yellow class, this is our decision boundary, this is our hyperplane for the red class, this is our hyperplane for the yellow class, and now we can see that these are the support vectors. So for yellow class, we have 2 perfect support vectors on a hyperplane, and for the red class, we only have 1 support vector. So this function help us to draw this situation or this condition in Python. So that was our data set, and we can see that this is our decision boundary. This is hyperplane for the red class, and this is hyperplane for the yellow class. Now we have 3 support vectors. If we want to see the coordinates of the support vector, so the function is svc.support_vector. Let's run this cell, and we can see that we have 3 support vector. Now, if we want to change this figure, let's observe again with the small value of C. If you remember here, the value of C is large, and we use large value as a 1. Now, let's draw these decision boundaries again with the small value of C, and here we have select the small value of C as 0.01. Okay, now let's run this cell. Now draw the plane. Okay, we can see that when the value of C is small, it means K is small. And we know from our theory concept, when K is small, then support vector machine will become a soft classifier. Now it is a soft classifier here. You can see that more and more support vectors want to enter into this prohibited area. Previously, when the margin was hard, there was no support vector here in that area between the decision boundaries and the hyperplane. At that time, it was a hard margin classifier because the value of K is large. Now here is the situation when we have put the value of C or K small, which is 0.01. In that situation, more and more support vectors want to join towards the decision boundary. And in that case, this is the soft margin classifier. So you can see that we have large number of support vectors now. And if we want to see their coordinate, so these are the coordinates of a support vectors now when it is a soft classifier. So till now, what we have learned in project 1. So if we go back and see what we have learned till now is that we learn how to create the data. After creating the data, we learn how to draw the best separating line. After that, we define a function. But before defining a function, we see the document of support vector classifier. We see what are the important parameters that can be input to the support vector classifier. Okay, now we use, then we define a function. Basically, we define a function that help us to create 3 kinds of hyperplane, that is a decision boundary and a hyperplane for each of the class. Similarly, this function also help us in order to draw the support vectors on the hyperplane. So basically, we want this situation to be happen in Python. Okay, so first we select the large value of C, and that value is 1, and we select the kernel equals to linear. When we use our function, we observe that for C is equals to 1, it was a hard margin classifier. In that case, there is no support vector machine or no support vector between the hyperplane and the decision boundary. On the other hand, when we reduce the value of C to 0.01, our support vector classifier becomes the soft classifier. And in that case, more and more support vectors want to join or come between the decision boundary and the hyperplanes. And in that case, we see that there are large number of support vectors. So this project is continued. I stop this lecture here. In the next lecture, I will continue this project 1. See you there.